Okay, so today we're going to do an episode on colorimetry and colorimetric analysis. And in the end, we're going to try to tie this all into the usage of Beer's law within our calculations. Um, and so this mini-series isn't really going to start off with any questions or any thought-provoking introductory ideas. I think I'm just going to delve right into it and start off with an introduction of what colorimetry actually is. Um, so, colorimetry is a field of chemistry that focuses on using the absorbance of specific substances to be able to actually determine what their compounds are and what their concentrations are. And now this all centers around the use of a colorimeter. Now, within that colorimeter, we're going to have a cuvette from which we place our substance into, and it's going to give us an output of an absorbance reading. Now, absorbance is essentially how much light that substance absorbs, or how much energy of that electromagnetic wave outputted is actually absorbed and doesn't make its way to the end or the other side of the colorimeter. And what the colorimeter actually does is has a specific energy output of the electromagnetic wave coming out one end, and it's going to go through whatever substance we have in our cuvette, and it's going to record the energy at the other end. And the energy difference is our absorbance value, and it's going to help us when we try to determine what concentration of the substance we have, what the compound is, and it's going to help us when we try to investigate reaction mechanisms, rate of reactions. We're going to try to figure out whether these reactions are zero order, first order, second order, and we're going to do this all using colorimetry. But what this actually requires is it requires us to have a reaction where there's a color change, where there's a change in absorbance, the thing recorded, because the colors we see and the colors of our substances is going to inhibit whatever light is trying to pass through. So if we say had a darker color, it's going to give us a higher absorbance value because it's going to be able to absorb much more light, versus whether we had a translucent or a transparent substance, that's going to give us a much lower absorbance. So what we normally have is it gives us an output of a graph of absorbance with time, and we have a reaction, say it's a first or second order reaction, and it comes down like this, and it sort of plateaus off where the reaction ends itself, where it terminates itself, and this is what output it's going to give us, and it's what we're going to use to try to figure out our rates of reaction and what order our reaction is. But the only way we can do this is if there's a color change involved, and this color change is seen through the change in absorbance from here to whatever our termination point is, the first time point at which there is no longer a change in absorbance marking the end of a reaction. And this can happen between reactants when they come together to produce a new compound that is sort of more translucent rather than opaque, or whether we have within our solution. So within our solution, we're gonna have our solvent, and we're going to have our solute. Now, the solute is what you add to the solvent that comes together to make a solution, and the solute is what you usually look at when we're trying to deduce colorimetry, because it's going to be the thing added, normally our colored substance that combines with our solvent to create something more transparent that marks the end of it being opaque, and instead giving us a clear solution. And so when we have a solute that comes together with a solvent, or gets substituted into a part of the solvent to create a final end product that removes the solute from solution and makes removes the solute from the solution and makes the whole solution colorless. That's when we're going to be able to use colorimetric methods to be able to deduce our rates of reaction. Now, this is where Beer's law comes in. Beer's law is given as A equals epsilon BC. Now, A is given as our absorbance, which is what we've already discussed. Absorbance doesn't really have a unit. Now, epsilon's interesting. It's what we call our molar extinction coefficient. Now, this is just a long fancy term, but it's a constant that is applied to each substance, and each substance has a specific molar extinction coefficient for each concentration of it, and for each wavelength at which you are recording absorbance. Because within our colorimeter, there's usually a few numbered presets, and basically each of these are going to emit a specific wavelength of light that's going to determine whatever molar extinction coefficient we have. So even if the same substance was at the same concentration, it would have a different molar extinction coefficient depending on whatever wavelength of light we were trying to pass through it. Now B is given as our path length, or length of cuvette. What this actually means is the distance that the light in our cuvette travels before reaching the other side, where we measure the change in energy. Now, most cuvettes are usually 1 by 1 by 4, so it's cubed, so it's a square at the bottom and it goes up by 4 cm. So our path length in this case would be light traveling from one vertical end to the other, so that would be 1 cm. Sometimes it's not even included within our calculations, but sometimes there are large cuvettes available, such as 4 cm. That's another common one, and I'm sure there's much larger ones too, if necessitated. And that's going to decide whatever path length we have. And finally, we have our C, which is our concentration of whatever substance we are trying to analyze, usually our solute, and this is given in moles per dm cubed. As usual, and it's going to be the independent variable within most of our rate examining mechanisms and experiments, whereas absorbance in this case would be our dependent variable. And so how do we actually calculate these specific variables? So what we actually do is we create what we call calibration curves. So calibration curves. The output given by our colorimeter is given as absorbance versus time. The only problem here being that when we want to find rates of reaction, we don't find it as change in absorbance over change in time. What we find a rate of reaction in are changes in concentration over change in time rather than absorbance. So what we actually try to find here is a relationship, a direct correlation between absorbance and our concentration, and we do this by constructing calibration curves. And calibration curves gives us this direct relationship by forming a linear line between absorbance and concentration. Thereby, if we know absorbance, we can find our concentration and vice versa. So what we usually do for this is we create standard solutions. Standard solutions, we take our solute, whatever's causing absorbance to change within our reactant solution, and we take different concentrations of that by by diluting it with distilled water. So we take our volarimetric flask, say we add a known amount of a known concentration of our solute, and we fill the rest up with distilled water until we reach whatever line or whatever volume of the volarimetric flask, and that gives us a known and fixed concentration, and we place that into our cuvette for placing it into our colorimeter. And what that will actually do, because it's a known concentration, it's just our solute, there's no reaction occurring, what it's going to do, this is if there was a reaction, but if there's no reaction and we're just placing the solute in, it's going to give us an unchanging constant value of absorbance for that particular concentration of whatever solute we're losing. Just imagine that's a straight line. And this is going to give us a specific absorbance for that concentration. And so if we plotted that on our calibration curve, and then we plotted our concentration, and we extrapolated both points, we'd be able to form a point in our line. We could actually just put pure solute. We know its concentration. We could just put pure solute into the cuvette, and we could find an absorbance due to that. And what this is actually going to give us is it's going to give us a linear line, linear relationship between absorbance and concentration. So say if we diluted it even more and it had a smaller concentration of our solute, it would give us a smaller absorbance, say here. And if we extrapolated that, it would give us something like that. And there's actually a y-intercept at this graph at 0. The reason for that is we calibrate it with just a cuvette, and we don't have anything else, because what we're trying to investigate is our solute. So thereby, if we had no concentration of our solute, nothing, there would be 0 absorbance within our colorimeter. So now if we drew a line of best fit, it would optimally give us a linear line, which I failed to draw here, but it would give us a linear line, a linear correlation between absorbance and concentration. And so what we can actually do from this is go back to our reaction. It's decreasing in absorbance due to time, due to whatever reaction our solute has with our solvent, and we're going to take 2 points. Now, we take 1 point at the start, and we take another point at the first time value at which absorbance stops decreasing, because that marks the end of a reaction. No more absorbance is decreasing because no more solute is being used up. It either has been all used up or all our solvent has been used up. One of the two has been a limiting factor, and that has caused absorbance to no longer change, and it's going to plateau out for the remainder. So we're going to take these 2 points. First time value is going to be our second point. Now, the reason we don't take a time value, say, in the middle, is because our rate of reaction would be different, say, from our first to second point versus our second to third point. Our second to third point, as you can see, has a slower rate of reaction. And so it wouldn't be fair to just justify whatever rate of reaction was going on from 1 to 2 or 2 to 3. So instead we take a gross general average from 1 to 3, unless, of course, we were investigating the rate of reaction from 0 to a specific point in time, say 2. If we were doing that, then that would be justified, but otherwise not so much. So we're going to take our general and our average rate of reaction from start to finish, 1 to 3. So what we're going to be able to do here is we're going to take our absorbance value at 1. We know time is 0. We know the absorbance value, so say it's up here. This is our starting absorbance, and we extrapolate this, and from this we find out our known concentration, which is called concentration U. Now, we go to point 3, the point marking the end of our reaction. It's also at a known time, and it also has a differing value of absorbance. So let's say this value of absorbance, and we find it on our calibration curve, and we extrapolate it, and we get this concentration. So it's called this concentration, V. From this, we can find our rate of reaction. Why? Because the rate of reaction is given as change in concentration over change in time. So what's our change in concentration? It would be U minus V over whatever this point in time was minus 0. So it's called this point in time x. So we have x minus 0, which is the same as saying x. So we have U minus V over x. And now this is our rate of reaction. And we know it's change in concentration over time. So that's moles per decimeter cubed per second. And this would be how we generally use colorimetric methods tied in with Beer's law to be able to deduce reaction mechanisms and rates of reaction.